Disadvantages of center tapped full wave rectifier. What is it? One disadvantage of this full wave rectifier design is the necessity of transformer with a center tapped secondary winding. Okay, center tapped secondary winding. What is the disadvantage of this? See, whenever you want to use the rectifier with high power applications, then center tapped rectifier, if you use it, its size will be more, and it becomes more complex. So size is increasing means automatically its cost will increase. That's why we do not prefer it. That's what I have written here. If the circuit is of high power, the size of the transformer will be large and expensive. Consequently, the center tapped rectifier design is seen in low power applications. So center tapped rectifier is having less ripple factor compared to half wave rectifier and good efficiency compared to half wave rectifier, but we cannot prefer it for high power applications due to the usage of this center tap transformer. Okay, this is the issue. Then what is the remedy? The remedy is the bridge type full wave rectifier. Why the name bridge? See, you can understand from the diagram itself. Here the four diodes are appearing like four arms of a bridge. It's as simple as that. Okay, and there are other ways of drawing this circuit. What are those ways? See, if you observe the diodes D2 and D1, they are in one direction, and D3 and D4 are also in one direction. Let me redraw it like this. Diodes D2, D1, in between the point A. Similarly, diodes D3 and D4, between them the point B. Between A and B, the AC power supply. So the transformer secondary winding or AC power supply, anything we can say. Yes. And one more thing, between D2 and D3, we have the point C, and between D1 and D4, we have point D. Between C and D, there is a load resistor RL, across which we are taking output from D to C, right to left, of course. This is another way of writing it. And there is one more way. Like here, all the four diodes are shown horizontal. Now I can show them vertical. D1, D2, D3, D4. Between D1 and D4, the point D. Between D2 and D3, the point C. D1, D2, point A, and D3, D4, point B. Between A and B, we are applying the AC input. Between D and C, we are taking output from D to C. That's it. See, this is the easiest way of drawing the circuit. It's very, very simple. Okay. Then further, what about its working? Right. Here, what I'm doing is, let me take this as Vs, which is equal to Vm sine theta. So its period is 2 pi. 0 to pi positive half cycle, pi to 2 pi negative half cycle of our secondary voltage. We can take so. Now coming to its working. What happens during positive cycles? Which diodes conduct and which diodes do not conduct? Let me erase this. Positive half cycle means here the positive sign is, this is positive and it is negative, means this is positive and it is negative. Look at the diode D2. Its cathode is connected to positive terminal of the supply, so D2 is off. D1, its anode is connected to positive terminal of the supply, D1 is on. D3, its cathode is connected to negative terminal of the supply, D3 is on. D4, its anode is connected to negative terminal of the supply, D4 is off. So what we can write here is during positive cycles, D1 and D3 are on and D2, D4 are off. Let me take that. Positive cycles means 0 to pi. During positive half cycles, that is 0 to pi, we can write D1 and D3 are on, D2 and D4 are off. So D2, D4 off means they simply act as open circuit. D1, D3 on, so there will be a flow of current through both D1 and D3. What about the current direction? See, current flows from positive to negative terminal of the supply. This is positive and here negative terminal. Okay, so the current starts flowing through D1 because here if you consider this point A, right, as it is open A to C, the current will flow through the diode D1, comes up to D. Next D to B, it is open, no current flows through the diode D4, entire current flows through RL, later it flows through C. Next once it reaches B, again from B to negative terminal of the supply. This is the direction of the current. Let me take this current as I. And what we can write for I1? I1 is equal to Vs, the secondary coil voltage, by secondary voltage divided by the coil's internal resistance Rs plus internal resistance of D1 Rf plus the load resistance RL plus internal resistance of diode D3 Rf, which further can be written like, instead of Vs, I am writing Vm sin theta by Rs plus 2Rf plus RL. Further, I can write it like Im sin theta, where Im is equal to Vm by Rs plus 2Rf plus RL. That's it. Like this we can write. And what about V output? Voltage across RL. This is I1 into RL. That is Im sin theta into RL. Done. Now let us see the waveforms. This is Vs is equal to Vm sin theta. It has a peak amplitude of Vm. And here D1 and D3 current. See, positive cycles I said D1, D3 are conducting. That is I1 is equal to Im sin theta. Okay, and no D2 and D3 are off, no current is flowing through them. Simply it is 0. And this current is from 0 to. I wrote here total current. Let me take this total current as IL, which is the sum of I1 and I2. I will come to this later. Next, V output. V output. It is Im sin theta into RL. So I can write it like some waveform. Its peak amplitude is Im into RL, where Im is equal to Vm by Rs plus 2Rf plus RL multiplied with RL. See, in center tapped rectifier, what we wrote is peak amplitude of the output is Vm into RL by Rs plus Rf plus RL. Instead of Rf, here we are writing 2Rf, nothing else. Okay, so this is what we can see from 0 to. I will come to this statement, IL is equal to IL plus I. Next, during negative half cycles, even though Vs polarities are shown like this, those are universal polarities. Okay, now negative cycle means, right, this portion. For this portion, it is like a negative source. Okay, voltage is negative means it is like connecting a negative source. Sorry, negative source means what should we do? This is plus and this is minus. Okay, negative sign. Then the positive sign is coming here, negative sign is coming. Look at D2. Its cathode is connected to negative terminal of the supply. D2 is on. And D1, its anode is connected to negative terminal of the supply. D1 is off. D3, its cathode is connected to positive terminal of the supply. So D3 is off. The anode of D4 is connected to positive terminal of the supply. It is on. Exactly opposite action. Earlier, D1, D3 were on. Now D2, D4 are on. Opposite action. Okay. Then what about the equivalent circuit? Negative half cycles. What we understood is D1 and D3 are on, D2 and D4 are off. Okay. So here D3 is acting like open circuit and D4 is also acting like open circuit. And what about the direction of the current? Current always flows from positive to negative terminal of the supply. So here the current is starting here and it is ending. It has to end at this point. So from positive terminal it is coming like this, and after reaching the point B, it goes through the diode D4. Next it flows through, after reaching the point D, it flows through RL. Next, after reaching the point C, it goes through the diode D2, and finally it reaches the negative terminal like this. This is the direction of the current. Let me take this current as I2. What can we write for I2? It is like Vs. So I2 is equal to, it looks like Vs by coil's internal resistance Rs plus internal resistance of the diode D4 plus RL plus internal resistance of the diode D2. It looks like this. But the reality is, what are the polarities of Vs? The Vs polarities are always from top to bottom. See, that is a universal convention we follow. Just to see the direction of the current only, I wrote this positive and negative signs. The reality is Vs polarities are, right, while writing the loop equations or node equations, we should take Vs polarities are from top to bottom, which means I should take here negative sign. Further, Vs is equal to my Vm sin theta by Rs plus 2Rf plus RL, which is further written like minus Im sin theta. And what about V output? it is I2 into RL, that is minus Im sin theta into RL. That's it. Okay, this is how we can write it. Okay, what is this negative sign? Okay, see whether it is positive cycle means Vs is positive, that time current direction is current through RL is from right to left. Then Vs, even though Vs is negative, then also the current through RL is from right to left. Means if I1 is positive, I2 is also positive, no doubt about it. Then what is the meaning of this negative sign? Because you see, Vs is negative and minus of Vs, minus Vs means the overall current I2 will be positive. That's it. Okay, if I write it like I2 is also equal to Im sin theta, then definitely, right, Vs is negative means Vs is negative cycle means current is also negative cycle, which is not so. Okay, this is the difference. You see, a simple thing, we can take it like this. If I take Im sin theta, I will write it in the next page. 0, pi, 2 pi, and I can say this current as Im sin theta. Okay. And what about I1? I1 is Im sin theta over the interval 0 to pi. This is true. And what about minus Im sin theta? What about I2? I2 is positive. The directions of I1 and I2 are same. And I2 is equal to, I2 is resembling minus Im sin theta over the interval pi to 2 pi. That is the meaning of it. Okay, ultimately I1 and I2 are positive. I1 is positive and I2 is also positive, but the equations are not same. Okay, this is what we can observe. And one more thing, I am writing IL is equal to, that is current through RL is the sum of I1 and I2. And what about IL? It is I1, IL is equal to, right, I1 is Im sin theta plus I2 is 0 over the interval 0 to pi. And it is over the interval pi to 2 pi, I1 is 0 and I2 is minus Im sin theta. That's it. Ultimately, IL is equal to, right, you can take it like this. IL is equal to I1 plus I2. Over the interval 0 to pi, it is looking like Im sin theta with peak amplitude Im. And pi to 2 pi, it is minus Im sin. What about V output during the interval pi to 2 pi? It is same as that of, it is also positive. IL is positive, automatically V output will be positive. Even though the output equation is looking like minus Im sin theta into RL, this is the output equation over the interval pi to 2 pi. So output is also positive. Again and again, I need not write. This is how we can show output voltage. That's it. So IL or V output are same as that of what we have got in shunt adaptive full wave rectifier. The analysis is also very similar. The equations or the waveforms are not changing, and the corresponding analysis, right, few things we can reduce, right, we can write without any further calculations. What are the things that we can write? see here. Anyway, I hope you get this point. Next, let me write IL is equal to, what is the period of output voltage or output current? It is pi. Input period T is equal to 2 pi and output period T dash is equal to pi. Whatever you have from 0 to pi, that is repeating. And here also its period is pi, T by 2. IL is equal to Im sin theta over 1 period. V output is equal to Im sin theta into RL over the limits 0 to 5. Same thing. Okay. Then what about the remaining calculations? What about IDC? We know, right? IDC is 2Im by pi. From the waveform, blindly we can write it. And VDC is equal to IDC into RL, which is further written like 2Vm by pi into RL by RS plus 2RF plus RL. From VDC, we can write the Thevenin's equivalent circuit. Bridge type full wave rectifier. That's it. Now you see VDC. VDC is equal to 2Vm by pi. This is 2Vm by pi divided by, okay, or 2Vm by pi into RL, okay, by RS plus 2RF plus RL. You can write it. So what is the, so looking into RL, the voltage looking into these two terminals is 2Vm by pi, which is our VThevenins, and the resistance looking into these two terminals, that is RS plus 2RF, which is our RThevenins, excluding RL. That's as simple as that. The Thevenin's equivalent circuit we can write with respect to DC. Thevenin's equivalent circuit of bridge full wave rectifier with respect to DC. Only DC. DC we have got, that's why we are able to write all those things. Here also I have shown DC source. Okay. Next, what about the value of RMS current? IRMS is equal to Im by root 2. I am not deriving all those things, not required. Then RMS value of AC component, unwanted AC or ripple component. It is IRMS dash is equal to square root of IRMS square minus IDC square. That is Im by root 2 whole square minus 2Im by pi whole square. Next one. Once we get these points, then the ripple factor and all. The first parameter is ripple factor. It is the amount of unwanted AC component by DC component. It is IAC into RL by IDC into RL. IAC by IDC. IAC means definitely at the time of substitution we write RMS dash by IDC. Anyway, if you further substitute and all, what we get, it is 0.48. Its value does not change. The second one is the percentage regulation. Again, it is VDC no load minus VDC full load by VDC full load multiplied with 100. If I further write it, I can directly write the answer RS plus 2 RF by RL minimum multiplied with 100. Straight away I am writing the equations. Okay. And third point, the percentage efficiency. It is DC power delivered to the load by AC input multiplied with 100. What is DC power delivered to the load? DC output power, that is IDC square into RL, that is 2IM by pi whole square into RL. And AC input power, it is just nothing but circuit power. It is written like IL square into RS plus 2RF plus RL. IL square means its RMS value, that is IM by root 2 whole square into RS plus 2RF plus RL. Then the percentage efficiency is equal to 4IM square by pi square into RL by IM square by 2 into RS plus 2RF plus RL multiplied with 100. IM square cancel. Finally, it is 81.2 divided by 1 plus RS plus 2RF by RL. That's it. It is same as that of center tapped full wave rectifier. There is no difference. Except instead of RF there, here we have 2 RF. That's it. The next one, transformer utilization factor, fourth parameter, I think so. Percentage TUF. Okay. Percentage TUF, if you take, that is DC power delivered to the load by PAC rated secondary. What is PAC rated secondary? It is just nothing but Vs into IL. Here I can able to write. Whereas in center tapped rectifier, I could not able to write. How can we write here? If you observe the circuit, see whether it is positive cycle or negative cycle, there is a continuity of current between these two terminals. Okay. So from this end to this end, whether it's a positive cycle or negative cycle, there is a continuity of current. The voltage between these two terminals is Vs, and the current that is flowing through this is IL. I can write. That's the meaning of it. See, just for your information sake, I am drawing all the three circuits once more. How I wrote this Vs into IL for that. If I take the half wave rectifier, the rated power of the secondary winding means what we rate PAC rated secondary. The voltage between the two ends of the secondary winding multiplied with the current that is flowing. We wrote it. At the end, later what we write, even though I wrote Vs, I wrote its RMS value, and RMS value of IL is IM by 2. This is what I wrote. And in center tapped rectifier, D1, D2, We wrote this is Vs and this is Vs. What happened? Positive cycles, the current is starting here but not ending here. If you take it, generally what we expect, PAC rated secondary, it is equal to, it looks like the voltage between these two terminals is 2 Vs multiplied with the current that is coming here is IL. Remember, we can't write it so. Absolutely wrong. Because see, IL is starting here but it is not ending here. Is it not so? Okay. And again, this is what? Positive cycles, the current is starting here and ending here. Negative cycles, the current is starting here and ending here. So how can I write 2 Vs into IL? It is meaningless. So what we did there, we took it as a combination of, right, a summation of two half-wave rectifiers. Instead of this, what we did is, it is 2 times PAC rated secondary of half wave rectifier. Alright, we have gone through all those things. Means the same parameter multiplied with 2. It is just nothing but Vm into Im by root 2. This is what we did. Right. There are some issues. But now, if I take this bridge rectifier, Vs, whether it's a positive cycle or negative cycle, there is a current flow, IL. There is a continuity of current for all time as far as the secondary winding of the transformer is concerned. Okay. IL is equal to Im sin theta over the interval 0 to pi and minus Im sin theta over the interval pi to 2 pi. That's it. But it is existing over one full cycle. 0 to 2 pi we have IL. And Vs is also existing. So what is PAC rated secondary then in this case? I can comfortably write the source voltage multiplied with the current coming out of the source. That is Vm by root 2 into Im by root 2. RMS value of Vs is Vm by root 2. RMS value of IL is Im by root 2. Vm into Im by 2. We can take. So, Vm by root 2, Im by root 2. Further, Vm can be written like Im into Rs plus 2Rf plus RL multiplied with Im means square by 2. Is it not same as that of our AC input or circuit power? Absolutely. When there is a continuity of current across the two ends of the source, then definitely under ideal conditions, the source power is equal to circuit power. The power delivered by the source is equal to power absorbed by the circuit. That's what you can see here. Source power and circuit power being same. In this context, if you take the efficiency in TUF, the numerator is not changing and denominator is also not changing, means transformer utilization factor is also equal to 81.2 by 1 plus Rs plus 2 Rf by RL. So the percentage TUF is same as that of percentage efficiency. Okay, that is why in bridge rectifier we need not worry about calculating TUF. Okay, we calculate efficiency, that is enough. That is, and transformer utilization factor are one and the same. We need not again calculate. Hence, no need to calculate percentage TUF in bridge type full wave rectifier. There is nothing to worry about the switching here. The source power is continuous and the current coming up to the source is also continuous for all time. And hence we can comfortably equate the power delivered is equal to power absorbed. Okay, this is the difference. So it is giving much better results compared to center tapped rectifier, and it has no center tap, and hence even for high powers also we can use this circuit. These are the advantages of bridge type full wave rectifier. And the next point is fifth point is peak inverse voltage. So for peak inverse voltage, again, just I'm taking according to our notation D1, D2, D3, D4. I do not remember. Let me check it once. Oh, D1, D2, D3, D4. Okay. The notation I followed there is anti-clockwise direction. D1, D2, D3, D4. Okay. Let us take during positive cycles. What we observed, anyway, this is RL. Okay, positive cycles, what we observed is D2 and D4 are of D1 and D3 are on. Let us take ideal case R. Okay, as D2 is off, what I am doing is I am just showing it open circuit. It is directed upwards, of course, and D3. Okay, nothing to worry about it. So I'm just changing the colors. Let me take it is VD2 from anode to cathode and VD3 from anode to cathode. Let us take this loop 1. Then what we can write? Right, I'm just taking the polarities like this, minus plus, no? Right, minus Vs minus Vd2 plus Vd3 is equal to 0. Neglecting the drop across D3, then Vd2 is equal to minus Vs. What is Vs? During positive cycles, Vs as usual, positive or negative cycle, Vs is Vm sin theta. Means D2 is off, and what is voltage across the diode D2? It is Vm minus Vm sin theta. It is experiencing some negative voltage. As it is experiencing negative voltage, it is off. And what is the peak voltage experienced by the diode under reverse bias condition? That is our peak inverse voltage. Magnitude of that peak voltage, that is Vm. Vm is peak inverse voltage. Or you can even consider the second loop, or we can take even this loop also, doesn't matter. Here D1 is on and D4 is off. As D4 is off, I'm just taking VD4 from anode to cathode, VD1 from anode to cathode. Next, if I take this loop 2, okay, loop 2 implies what we can write? Minus Vs plus Vd1 minus Vd4 is equal to 0. Neglecting the drop across the diode which is in conduction, Vd4 is equal to minus Vs. That is minus Vm sin theta. So D4 is also experiencing negative voltage. That's why it is not conducting. It is open circuit, no? And peak or the maximum voltage experienced by diode D4 under reverse bias condition, the peak voltage, it is Vm. That's it. However you take here, the first one is loop 1 and second one loop 2. Anything you can consider, the result remains the same. Similarly, you can try with negative cycles also. Doesn't matter whether it's positive or negative cycle, the result remains the same. And the next one is the sixth one is the ripple frequency. That is the frequency of the unwanted AC ripple. That is nothing but 2 times the input signal frequency. We are well aware of it. Okay, that's it. It's very, very simple. Already sent it up rectifier. Okay, that's about the analysis of our bridge type full wave rectifier. Okay, you may be getting a doubt like what happens if input and output are exchanged? In this case, is the circuit fixed? Yes, it is. See, in this bridge type full wave rectifier, if I interchange input and output, what happens? Our regular circuit is like this. Okay, here we take the output. Now instead of output, I am writing input. Let me take Vs here. Along with that, I am taking here some resistance Rs. Right, it should be must. I'll tell you what is the reason. And here I am connecting RL. And Vs polarities are from top to bottom. So V output polarities are also from top to bottom. And here output polarities are taken from right to left. I am taking Vs polarities are also from right to left. Here it is D2, D1, D3, D4. What I did is I interchanged input and output in the bridge rectifier. How it works, I want to check it. Okay. Then during positive half cycles, positive so here it is positive and it is negative. Look at the diodes D1 and D4. Its cathodes of D1 and D4 are connected to positive terminal. So both D1 and D4 are off. What about D2 and D3? The anodes, their anodes are connected to the negative terminal. So D2 and D3 are also off. No diode conducts. So all the 4 diodes act as open circuit. RL. So positive and negative terminals of this. Is there any current that is possible through RL? If I take this current as IL, because output polarities are from top to bottom, IL is simply 0. No diode conducts and no current flows through RL. This is what we can say. Okay. And what about during negative half cycles? Exactly opposite action. Positive cycles, no diode conducts. Negative cycle, once you change the polarities of the source, definitely all 4 diodes will conduct. Okay, let us check it. Here it is minus and it is plus. So negative sign is coming here, positive sign. Look at the anodes of 4 diodes. Anodes of D2, D3, they are connected to positive terminal. D2 and D3 will be on. and cathodes of D1 and D4 are connected to negative terminals. So D1 and D4 are also on. All the four diodes connect. Okay, so that the equivalent circuit, if you take so further, look at the direction of the current. Anyway, it is minus and it is plus. So suppose this current is IL. If I take it, whatever the current that is leaving the source, the same thing has to enter. This also should be IL. Okay. So assuming ideal diodes, IL is divided into two equal halves. That means IL by 2 and IL by 2. Here D1 and D4 are okay conducting, and this is IL means, and if the diodes are identical, then this is IL means this should be IL by 2, and this is also IL by 2, which means whatever IL by 2 comes here, the entire IL by 2 has to go like this, and whatever IL by 2 comes here, entire IL by 2 has to go like this, which means the current through V output is simply 0. See the interesting thing. Okay, this is one way of concluding that V output is 0, whether it is a positive cycle or negative cycle. Okay, here V output is simply 0. Here also it looks like V output is 0. Or in other words, another way of concluding it. Okay, I'm just redrawing the circuit. Okay, then if you observe this, ideal diodes, we can assume, or if you assume the diodes resistances are same, then okay, or here itself we can conclude it, not an issue. Once it looks like all the four diodes are ideal, means it's like a balanced bridge. Once the bridge is balanced, what is the output here? Then output is taken across RL, right? This potential, the potential here and the potential here will be same. In that case, output is simply 0. In that way also we can see. Okay, it is like a balanced bridge. See, I can bring this combination outside and bring this combination inside. Then it looks like a balanced bridge zone. Is it not so? Once the bridge is balanced, then right, because all the diodes are conducting, they are not a short open circuit, they are maybe short circuit, or once they conduct, practically they may offer some resistance. Assuming identical diodes, all four diodes offer a resistance, or and it is like a balanced bridge. Or for better understanding, I am redrawing it. D2, D1, D3, D4. There are multiple ways to conclude it. I am bringing this RL here and Vs here. That's it. So now here each diode is acting like, right, again, right, I can write D2, D1, D3, D4. So if you look at diodes D1, D2, D3, D4, this combination is acting like a balanced bridge zone. Okay. In a balanced bridge, once all the resist, right, what happens, this voltage, I can take this point as VC and this is VD. VC is equal to VD implies V output is 0. No doubt about it. Because here each one offers a resistance RF. It is perfectly a balanced bridge. Again and again, I am not interested to draw the circuit. That's why I'm just showing RF. All the four resistors are equal in a balanced bridge. Automatically, right, what we can see here is the output is, right, from Vs, the current coming from Vs, I took it as IL, and the same thing has to enter here. Means this is IL by 2 and this is IL by 2. Again, the same IL by 2 current goes like this and the same IL by 2 current goes like this and join together. And is there any current that is possible through this? It is simply 0. In this way also we can check. Okay. Then what is the purpose of this RS? Okay, everything is fine. You can see as a bridge, balanced bridge, or you can take the currents and all, right? However you take it, it is true. Okay, positive cycles, no diode conducts, output is 0. During negative cycles, all four diodes conduct, still the output is 0. And what for this RS? See, in this circuit, suppose RS is not present. I'm just taking Vs only. Anyway, negative cycles I'm taking, right? It is on, it is on, it is on, and it is on. All are acting like short circuit. Short circuit. Ideal case I'm taking. Short circuit. If that is the case, what is the voltage between these two terminals in this direction? Almost it is 0. Or practically, if you take instead of short circuit, if you take it, right, you can take short circuit also, it doesn't matter. And voltage across this will be 0.7 volts from anode to cathode. It also maintains 0.7 from anode to cathode. This maintains 0.7 from anode to cathode. This also maintains 0.7 from anode to cathode. Means if you see in this direction, the voltage between these two terminals is 1.4 volt. And in this direction, if you see 0.7 plus 0.7, 1.4 volt. Which means, again, if you see in this direction, it should be equal to Vs. Is it so? It looks like Vs is equal to 1.4 volts. Is it so? We do not know. We know Vs is Vm sin theta. It may be 5 sin theta, or it may be 10 sin theta, or it may be 20 sin theta. Who knows? Is it possible to say 5 sin theta is equal to 1.4 volts? Impossible. Wrong. Okay, ideal diodes means short circuit, then 5 sin theta is equal to 0, or 10 sin theta is equal to 0, 20 sin theta means diodes will burn, an imbalance equation. So what to do? To protect our diodes, to avoid that short circuit, we need to place here a resistance. That's why I showed there some resistance RS. That will take care of that balancing of our circuit equations. Then we need not worry. Okay, there is some drop across RS. Okay, so that will automatically take care of the remaining things. That's it. That's why the resistance RS is kept here. Without RS, the circuit is invalid. RS, it may be right 1K or 2K, what depends. Right? It's not like source internal resistance. Some resistance we need to keep to see that the bridge is, sorry, the circuit is proper. Okay, that's it. That's about the bridge type full wave rectifier.